Okay, let me just turn on the laser pointer. Yeah. So we are good to go. So hello guys, welcome all of you to one more live problem solving session for the course Fundamentals of Semiconductor Devices, which is currently being conducted by Professor Digbijoy Nath from IISC Bangalore. Just to introduce myself again as a formality, I am SOHAM LAKHOTE, currently a fourth year Ph.D. student at IISC Bangalore, and my research area is in the field of analog and RF circuits, right? So now this is just the normal organization. We will have a first session of 50 to 60 minutes. Then we will take a short break, and again we will resume our session in the part 2, right? And just for the formality purpose, like all the recordings are being uploaded in on this YouTube channel, and this Excel sheet has been made available in the course page, right? So you will be able to access each and every lecture through that Excel sheet. And in each and every video, in the description section, I always put a link to the Google Drive folder where I'm actually uploading all the lecture notes, right? So I hope this is very much clear. And so now I guess we will start the session, but before solving the problems directly, we'll just have a very quick recap which will help us to solve few problems in this session, right? So we had studied everything about the MOSFET, that is metal oxide semiconductor field effect transistor, in this week, right? So now let's have a quick recap, right? So now let me just turn on my pen, right? So as you know, this is our cross section. This is our cross section of the MOSFET, right? And if you just look at this part, just this part, right? So now you will easily see that this resembles your MOS cap, right? This resembles your MOS cap structure, right? So now what is the reason why we have even putted these two N plus regions over here? So you remember sir must have told you, right? So sir must have told you something about the transistor, right? So what is exactly the transistor? Like there are maybe let's say three terminals over here, and you apply a voltage at this particular terminal, and you control the current that is flowing over here. You control it through the voltage. So your I naught is nothing but, let's say this is your V naught, so I naught is nothing but function of V naught, right? So what does this mean? If I am applying a voltage at a third terminal, let's say this is my third terminal, let's say this is my first terminal, and this is my second terminal. Sir must have told you this long time back when he was teaching the BJT, right? So the job of the transistor is to control the current using the voltage which is not applying between the two terminals where the current is flowing. I will repeat it. The two terminals, that is the first terminal and the second terminal, is the terminal where the current is flowing in between those terminals, right? So the job of the transistor is to control this current using the voltage which is not applied at those particular terminals. So I'm applying the voltage at third terminal and my current is getting flowed between the two terminals, right? So now let's imagine this is my MOS cap, right? So now let's imagine this is the VG that I'm applying, right? This is the VG that I'm applying, and now what I want to do, so my job is to create a MOSFET. My job is to not create the MOS cap, but job is to create the MOSFET, right? And now what is the MOSFET? This is the basic principle. The current should be controlled by the voltage applied at the third terminal, right? Now what happens when I apply the VG over here? This is a P-type region, right? The moment I apply, let's say if I come over here, right? This is the condition that I want to have. Let's say VG is positive and it is greater than VT. Now you know what is going to happen in this case, right? There is going to be a depletion region that will be created. This has been shown in this part over here. This structure that you are seeing over here, this dash line that over here. So this is nothing but your depletion region, and this blue dashes that you are seeing. So these are your actually electrons. These are your free electrons that are actually present. Now what has happened? The voltage that I applied over here, it created an inversion layer that is present over here. So now what happened over here? If you look over here, for example, in this case N plus and in N plus over here. So I will draw them separately. This is N plus and this is N plus, right? Initially there was nothing in between. So it does not matter if I apply a particular voltage over here, like between these two terminals. This, let's say this is VD and this, let's say this is VS. Nothing is going to happen because there is no free carriers that can move in between these terminals, right? The current is nothing but the flow of electrons, right? There should be flow of electrons from here to here, but I already told you there was nothing in between. Now I have created sufficient number of electrons between my source and drain. And how did I do that? By applying the voltage at the third terminal. And why did I apply the voltage at third terminal? Because this is what the transistor is supposed to do. Apply the voltage at third terminal, control the current between first two terminals, right? So now this is I have done, and I have created electrons over here. I have created a surplus of electrons over here. The moment I apply any voltages between these 2 points, now it will start the motion of electrons over here, and the electrons will start flowing. That's why the current will start flowing between these two terminals. So first of all, by applying the voltage, I have created a free carriers over here, and by applying the voltage over here, I am able to control the current, right? So this is how this MOSFET actually works, and this was the basic principle. This is why we studied the MOSFET first, because principle of MOSFET is the thing where you understood that there is a something called as the depletion region, and there is something called as the inversion layer. We have created the inversion layer over here. Now this inversion layer will help us to get the current across this device, right? So I'm applying the VG over here, but I'm getting the current over here, right? This is the movement of electrons that is I'm showing in this direction, and the direction of current will be in the opposite direction, that is the ID. And this is the same thing that is shown over here, right? So I hope this is very much clear to you. And now by the way, just for the sake of clarity, like why there is a depletion region over here. If you look, for example, just look at my cursor, there is a depletion region that is also present over here, right? So now what is actually happening, if I just take this part, it is nothing but my P and N plus junction. And you very well know what actually happens when you join the P and N plus junction. You will by default, without applying any voltage, you will get a depletion region, right? And depletion region will be more on the P side because N side is heavily doped. That's why you can see there is no depletion region that has been shown in the N plus. Obviously there will be some depletion that will be there, but its width will be very small because that region is heavily doped, right? So that's why you can see all the depletion region is shown on the P side over here, and nothing has been shown inside the N plus, right? This is the reason, right? And similarly over here in the N plus, now you will see that the depletion region on this side, if I just highlight for this particular area, right? And again I will take this junction P and N plus. Now what is actually happening? See, you can see the width XD over here, it is higher than this smaller width, let's say XD1, and this is XD2 over here. So you can see XD2 is higher compared to XD1. Now why did this happen? The only case where the depletion region width in the PN junction will increase in the case of the reverse bias, right? Now what I have written over here, it is nothing but the plus VDS. That means I am applying a positive voltage on N plus side. So the moment I am applying a positive voltage on the N type semiconductor, right? So this is nothing but the condition of the reverse bias for the PN junction, and that's why you can see the depletion region will increase because this PN junction is now under heavy reverse bias, right? So that's why you can see the depletion region over here on this side is higher compared to on the left side over here. So I hope these are the few points that I just wanted to make clear, because these are generally not written in any books. If your basics are clear for the PN junction, then you will be easily able to interpret it, right? So I hope till this point it is very much clear to you, right? And now what did we see? Okay, this was our structure, right? Now we have transitioned from something called as the MOSFET to the MOSFET, right? We understood the need of the transistor. We first created the MOSFET, and from there we transitioned into the MOSFET, right? Now we have this structure, this basic structure of the MOSFET with us. You can see it is a 4-terminal device. It has a gate, it has a drain, it has a source, as well as it has a body, correct? And now what is of interest to us? There are two things that are of interest to us, right? One is ID versus VGS characteristics, and the second is your ID versus VDS characteristics, right? So these are the two things that we generally want, and these are not only interest for semiconductors, but you will clearly see all of the circuit designers will be using these two characteristics when they design the circuits, right? Because there is something called as the transconductance. I don't know whether sir has told you this or not. There is something called as the GM of the transistor, and now it is nothing but your dou ID by dou VGS, right? And now this GM that you are seeing, it actually determines the gain of the MOSFET. You will see this when you study the circuits course, right? I'm just giving you a little bit hint, like why do we even want to plot ID versus VDS, right? And ID versus VGS. So I'm just giving you some hint that how these characteristics will actually help you when you want to determine the gain of the circuit, right? So this was just one of the parameters that actually comes out from these characteristics, right? So now this is the output, that is ID versus VDS characteristics that I have plotted over here. Sir must have told you, right? So there are 3 regions of operation normally. If you just ignore the short channel effects for now, which sir must have told you in the last lecture of the current week, right? So we have 3 regions. One is your cutoff region, correct? the next one is your linear, and the next one is your saturation. Correct. So now what this curve is showing over here, right? So I'm just highlighting the two regions over here, right? So this parabola that you're seeing over here, I hope sir must have explained you this. So this line is nothing but your VD sat, that is your VGS minus VT line, and all of the right side, for example this complete right side that I'm showing you over here, right? So okay, so there was some doubt was there regarding the what is the use of the bulk terminal, right? So now you must have studied that substrate bias effect, right? So if you ask circuit designer what is the use of this bulk terminal, then I will generally say this is a symbol of the MOSFET. This is a body terminal that you have, right? We guys generally we generally short it with the source, and we generally connect it to the ground, right? But what if you have a circuit like this? For example, let's say this is the MOSFET. Let's say you put one MOSFET on top of the other MOSFET, right? Then what is going to happen? This is the body voltage, and this is the body terminal, and this is the source terminal over here, and this is the drain terminal, and this is the gate terminal, right? So generally if you ask circuit designer, then we generally say that we generally what you can say, the short the body with the source, right? But there are few circuits where you apply certain different voltage to the body compared to the source over here. So I won't go into a lot of circuit details, but I will just tell you, I just told you about this term GM over here, right? This GM is nothing but dou ID by dou VGS, right? And so this dou VGS, you can also write one more term GMB, dou ID divided by dou VSB, right? Now what happens over here? Now why I have defined this term? Because this GMB, right, it helps you to give extra transconductance. So now if let's say you have a GM and you have a GMB, now if you need a lot of higher GM from the circuit without increasing its size, see this GM that you are seeing over here, it's proportional to W by L, right? Now you don't want to increase the size of the transistor, but you still want to get the higher GM, right? So now what you do, you also apply a voltage to the body terminal as well, and you get something called as GM plus GMB. I won't go into the details right now, but just understand that it helps you to get some extra transconductance. And when you study the circuits, especially the MOSFET circuit, like analog VLSR, some subjects like that, you will be able to see some circuits where we actually use this body terminal over here. So I hope this point is very much clear, at least as of now. When you go to the circuits course, it will become even more clear. But I have just given you some hints like why we have this body terminal that is present over here, right? And one more thing, if you want to ask from a semiconductor point of view, then what is my operation of the MOSFET? I want to get the current flowing like this ID, right? I don't want any current to flow in this direction, because this is nothing but, let's say this is I1 and let's say this is I2. See, I don't want my current to flow like this. I just want my current to flow between the drain and the source, right? So now what I have to do, see, this is a PN junction. This is a PN junction, N plus and P type over here. Now coming to your question, if I don't have this body terminal, then what is going to happen? I will tell you, just a minute. Let me check if I have a space over here. Let's say this is my P, let's say this is my N plus, right? Now this P, this is your V body actually, and this is your V source, right? Now you are telling me that don't take this terminal at all, right? Now this terminal will be left as a floating terminal. See, when you apply something, when you want to apply some voltage to the node, like you generally connect it to the voltage source, right? And then you apply certain voltage. Let's say this is my V battery. Let's say this is my V battery, correct? Now you are telling me don't connect anything over here. Don't even take this terminal out. That means this node is left floating, and it can take any voltage. It can take any voltage because it's a floating node. You must have studied in the subject electrical networks, right? The node should not be left floating in the circuit, either connected to ground or either connected to particular voltage. Now if this voltage is such that, let's say, it becomes a very what you can say, a very higher voltage. Let's say my VDD is, let's say, 2 volts, my ground VSS is 0 volts, right? And this voltage, this VB, if you left it floating, let's say my VB becomes 1.5 volts. Now what is going to happen? This is my P, this is my N plus, right? This is my VB that you left floating. It is taking the value of 1.5, and this is my V source, right? And let's say I have connected it to ground. Now what happened over here? This is my PN junction, right? And now you have forward bias this PN junction. I hope you are getting the seriousness of this body terminal, right? it can take any voltage, and if it took the voltage of 1.5 volt or higher, or maybe even 1 volt, then this PN junction, you have forward bias this PN junction actually. And did you want to do that? Definitely not, because I don't want, I already told you, right, I don't want any current to flow to flow like I1 and I2. I only want a horizontal current, I don't want any vertical current in my device, right? So now this is the answer that semiconductor guy will give you. Like this node will become floating, it can take any voltage. I don't want this node to have any particular voltage, so that's why we generally take this body terminal and we short it with respect to the source, right? So this body and the source that I already told you, right, this is the body terminal, this is the source terminal, we have shorted them together, right? So the circuit design will give you, okay, I may get some extra transconductance, right? The semiconductor guy will tell you, I don't want any particular voltage, I don't want this PN junction to be forward bias, so I have to always make sure that it is always reverse bias. So that's why it is very much important to take this body terminal out and give it a defined voltage, a defined voltage. I don't want this terminal to be floating. I hope the answer must be clear to you till now, right? So now let me move forward. So now what is happening over here? I have written two current equations, right? I already told you there were three regions. One was the cutoff region, one was the linear, and another one was the saturation region, right? So now this right side, that where I have highlighted over here, right? So now this is what is called as the saturation region, and the side that is left to it, this left side that you are seeing over here, assuming that your VGS is greater than VT, then this is called as a linear region of operation, right? And now the current equation in the case of the saturation region, sir must have told you these equations, I'm damn sure about it. This is the saturation region and this is the linear region. These are the equations of current for the saturation and the linear region, right? Now the interesting thing to see over here is that for the saturation region, the ID is just dependent on the VGS. Now what did I tell you? The sir must have told you the, like, why we even wanted to create the transistor, right? We apply a voltage at the third terminal. We want to control the current between the between the two terminals by applying a voltage to the third terminal. Now just see what is actually happening. The current ID, it is flowing between drain and source, right? And this VGS, right? This VGS, assuming that the source is grounded, now this is applied at the gate, right? So now by applying the voltage at the gate, I'm controlling the current between the terminals drain and the source, right? This is what this equation is telling you, right? So if you want to actually get the transistor action, that is the amplification action, right, then you generally operate the device in the saturation, because if you look on the right side, then the ID that you are seeing over here, it is not only dependent on the VGS, but it is also dependent on the VDS. And this violates what I wanted to do with the transistor, right? Because I don't want, let's say if you go over here, this is your first terminal, this is your third terminal, this is your second terminal. Now if the current between the first two terminals starts depending on the voltage that I am applying between these two terminals, then it is not of use to me, right? So that's why for amplification purpose we never use the transistor in the linear region, we always take care of it in the saturation region, right? So I hope till this point it is very much clear. I have further slides regarding the saturation region and all, but we will go there as our lecture progresses, right? Now coming to the important point, you will tell me, okay, you have told me like the transistor has three regions. One is the cutoff, one is the saturation, another is the linear region, right? But how do I even identify these regions, right? Because first of all, I have to set up certain bias condition. I have to apply certain VGS, I have to apply certain VDS. And how will I select these values? Let's say I want to operate the transistor as an amplifier in the first case, right? And in the second case, I want to use it as a switch, right? Then I have to know what values I should apply as VDS as well as the VGS, right? So now coming to this point, this is one term called as the VDS saturation, and its value is equal to VGS minus VT. Sir must have told you this, right? Now if you apply VDS greater than or equal to VGS minus VT, then sir must have told you that we operate the transistor in the saturation region. You know what happens to the channel, right? The channel gets pinched off, right? And the channel even starts to move. You won't be having a continuous channel between the drain and the source. There is a region where you won't get a channel at all, right? So this is called as saturation region. And now in this region, your MOSFET behaves as a voltage controlled current source, right? The voltage is controlled at the third terminal and you get the current between the first and second terminal, right? And this is what I have written. It is used for the amplification purpose, right? If you want to so for the amplifier, just a minute, where is my cursor? Yeah, so for the amplifier case, you operate it in the saturation. If you want to operate it as a switch, right, then you operate it in the linear region, right? So now what do I mean by linear? So you must have seen there is a cutoff region and there is something called as a linear region. So now when the MOSFET is off, it is under the cutoff region. When the MOSFET is on, it is under the linear region, and that's how your switch, and that is how your switch, that is how the MOSFET behaves as a switch, right? And now in this region, your MOSFET actually behaves as a voltage controlled resistor. Now what is this? This is, you must be hearing this for the first time, the voltage controlled resistor. So if you look in this equation, right, the ID is equal to your mu n Cox omega by 12 2 times VGS minus VT VDS minus VDS square. So now your ID, right, it is actually depending on the VDS as well. It is depending on the VGS as well, right? So now if I want, let's say this is my MOSFET. Let's say this is my MOSFET, right? So now what did I tell you? This MOSFET between these terminals, drain and source, it will behave as a resistor, but it will be a variable resistor, right? It will be a variable resistor and its value will depend on your ID actually. So now how to calculate this resistor, this ID you have as a function of VDS and VGS, right? So if you take, so now what is R? R is nothing but your what? V is nothing but your IR, right? V is nothing but your IR. So if I just take from Ohm's law, R is nothing but your V upon I, right? So now ID is a function of VDS and VGS. Since for a resistor, a current that is flowing into the resistor is nothing but the function of the voltage that I am applying across the resistor. Let's say this is my terminal A. Let's say this is my terminal B. So whatever voltage I will apply between the A and B, my current will be depending on that value, right? So now if you just take dID by dVDS, so just differentiate this ID with respect to VDS actually, and just take the inverse of it, you will get the resistance over here. So I'm just giving you intuition. My aim is not to derive the equations at this stage, right? I'm just telling you how it is behaving as a voltage controlled resistor. So the resistance is nothing but the, if I apply the voltage between the drain and source, my current ID that is flowing over here, right, it should depend on the this VD and VS, right? So that's why I told you just take this ID as a function of VDS and VGS. And how will you take that? You will use this equation that I have shown in the last slide, right? And you will just differentiate ID with respect to VDS over here, and you will get the value of the resistor. And now that resistance will be very small because MOSFET is in the on condition, right? So what is the job of the switch? When the switch, right, when the switch is on and when the switch is off, switch is on, it offers low resistance, right? It offers low resistance, and when the switch is off, it offers very high resistance. Correct? I already told you my MOSFET is on, so my switch should have a very low resistance, and when my MOSFET is in the off condition, it will give me a very huge resistance, right? So I hope till this point it is very much clear to you, right? And now this is one common question that is generally asked in many interviews when you go for MTech or PhD interviews, or even for any job interviews or something like that, right? So they generally ask this question like, how does the current even flow in the saturation region, right? Because why they ask you this question, I have few slides afterwards, but let me just give you a quick intuition, right? So now I'm just taking a MOSFET structure over here. I'm just highlighting this parts over here by source as well as the drain over here, right? Similarly for all the three diagrams. Now why they ask this question is because sir must have told you that as you keep on increasing the VDS value, right? As you keep on increasing the VDS value, this channel that you are seeing over here, this channel, it actually starts to shrink at the drain side over here. And now if you ask me the reason why this shrinks, then sir must have told you that, and I have derived it in my last lecture as well, the channel, the inversion layer charge, this is my inversion layer, right? So the inversion layer charge that is present, it is proportional to your VGS minus VT minus Vx. Now this, what is this Vx? Vx is nothing but the potential that you can see in this channel. So this is my Vs, this is my Vd. Since they have converted it to 0, right? So my Vx at x equal to 0 is equal to 0, and my Vx at x equal to L. L is nothing but my channel length, right? This is my channel length, correct? I hope you agree with me. This is my channel length. So at Vx at x equal to L is nothing but VDS, right? And now you know this VDS is always positive. This VDS is always positive, right? So if I'm applying, if I'm increasing the VDS, that means I'm increasing the Vx at this end, at the drain end, right? So if I keep on increasing the value of Vx, right, there will come one point where this term that you are seeing over here, it will reduce down to 0, because my Vx is having a negative sign, right? And the moment this term becomes 0, right, we call that point as a pinch off point, and your channel actually just reduces to a single point at this end. And if you keep on increasing, this, right, then what actually happens, there your channel is there, right, your channel is there at this point, actually shifts to the left side, and there does not exist any channel on this particular side. Now the question comes, okay, there was an inversion layer that I had created, but now you are telling me that there will not be any inversion layer that will be existing in this particular region near the drain side. Now how the hell will current flow, because I have completely removed the inversion layer? So I will write no inversion layer. So now if there is no inversion layer, then how will I even get the current? So this is one question that they generally ask in the job interviews or in the PhD or MTech interviews, right? So what is actually happening over here? See, I have a depletion region, right? Even though I don't have any inversion layer that is present, right, but my field is so strong over here, right? This value that you are seeing, let me just give you a very small hint. L is your, let's say, 1 micrometer. Then your this gap that you are seeing, let me highlight this gap as delta L. This delta L that you are seeing, it won't be, it will be even, I guess, less than 15% of your L value, right? So now what is actually happening, this delta L is very small, so you can see this delta L, like I have certain potential over here, right, and my L is very small over here. So now what is the formula of electric field? Is nothing but V upon L, right? If I am applying a potential and my L is very small, L is very small, right? So now I will get a huge electric field in this region, and because I have a huge electric field in this region, now because of that, my electrons that are coming from the source to drain, they will actually get swept away towards the drain region, right? And that's how the current actually flows, right? So this is just the statement that I have taken from the Donald-Niemann. By the way, all the diagrams, most of the diagrams I have taken, even if I have not written the references, they have been taken from the Donald-Niemann book. So you are welcome to go there and to study all these concepts in the depth, right? So this is the same thing that I have written over here in the statement. You can read it when I will share the notes with you, right? So now I hope till this point it is very much clear to you. Now we will start solving the problems, because we will start solving few sets of problem first, because we have cleared each and every concept that are required to solve these problems, right? So now let's see what is the problem number 1. So now the parameters of the N channel silicon MOSFET are, they have given the mobility, they have given the thickness of the oxide, the W by L value is given to me, the threshold voltage has also been given to me, right? So if the transistor is biased in the saturation region, then find the drain current of for the VGS equal to 1.2 volts. Now first of all, I have to see in which region the transistor is biased, right? They have already given me the transistor is biased in the saturation region. So what is the formula for current in the saturation region? It is nothing but half mu n Cox W by L into VGS minus VTH the whole square, right? We do see, whenever in the question they have not mentioned anything about the channel length modulation, this is the by default formula you have to use, right? So I'm not, so there should have been one more term, 1 plus lambda VDS, right? But this term is complete 0 over here. This lambda VDS term is 0, because there is no channel length modulation that has been given in the question, right? So now let's see if we have everything we want to know. See, we currently don't have the value of Cox, right? We have to find the value of Cox, and how to find Cox is nothing but epsilon ox by Tox. And what is epsilon ox? 3.9 into dielectric constant of the free space, right? 8.85 into 10 to the power minus 14. What is the value of thickness of oxide? They have given 8 nanometers. I have to convert it into centimeters, so that's why I'm multiplying with the 10 to the power minus 7 factor. Now this value, if you calculate, this will come out to be around 440 into 10 to the power minus 9 farad per centimeter square. This is capacitance per unit area. Please remember this thing. So now once we know this, now we are good to go with the equation number 1, because we know everything in the equation number 1. So let's start solving it, right? So now ID is nothing but half into, what is the value of mobility they had given? 650, right? 650 half into mu n into Cox. What is the value of Cox? 440 into 10 to the power minus 9. 440 into 10 to the power minus 9. half mu n Cox. What is the value of W by L? It is given as 12 into VGS minus VTH. See, VGS has been given as 1.2 volt, VT has been given as 0.4 volts. So VGS minus VTH will be what? 1.2 minus 0.4, that is 0.8 volts, right? So now if I just substitute 0.8 over here, this is 0.8 square. So now if you just calculate this value, right, this ID value, this will come approximately as 1.098 milliamperes. And this is generally the value that you will be getting most probably like when your transistors are operating in the saturation region, right? So generally from 100 microamps to few milliamps. So this is normally the range when your transistor is in the saturation region, right? So this will be the range of the currents that you will be getting depending on what is the value of width by length ratio that you will choose, right? So I hope this question is very much clear. Again, a very easy question. There was no trick in this question, right? So now we will solve few MCQs, right? Because they will help us in understanding few of the concepts that we had just studied, right? So now first question is for an ideal P-type enhancement MOSFET. So there were actually two types of the MOSFETs, right? So there were two types. One was the depletion region MOSFET. If sir has not taken, then don't worry. Like even we won't be considering it for this course. And one is the enhancement type MOSFET. So most of the MOSFETs by default, whatever you will study in the book, actually they are the enhancement type MOSFETs, okay? So that's what has been given in the question. For an ideal P-type enhancement MOSFET, choose the correct statement. So now they have not given the NMOS, it's a PMOS actually. So what is a PMOS? Let me just draw a very quick cross section, right? So now this is my oxide, correct? And now this is my gate, right? Now this is a PMOS, right? So my substrate is not a P-type anymore, it's a N-type. And this N plus regions that you had actually, they will become now P plus regions, right? They will be becoming now P plus regions. Now they're asking us, like, see in the options itself we are seeing inversion layer, inversion layer, inversion layer. So we know now that we want to create an inversion layer over here. My substrate is N-type, the inversion layer will consist of holes, right? I hope you agree with this. These are nothing but your holes, right? And to have a holes over here, right, to have a holes, first of all I have to create a depletion region, right? And to create a depletion region I have to push away the electrons. See, there were few electrons before creating the inversion layer. There were few electrons, right? And I wanted to push the electrons into the bulk region, and the only way I can do that is by applying a negative voltage, right? The moment I apply a negative voltage over here, what is going to happen, right? What is going to happen? This negative voltage that I have, negative charges that will be accumulating on this metal plate, they will push away the electrons. They will push away these electrons into the bulk region, right? And I will get the depletion region. And if I make it more negative, like if I increase this negative value, then there will come a point where I will create the inversion layer of holes, right? And it makes sense because this I am accumulating a lot of negative charges on the metal and I am getting a lot of holes over here, right? So you know how the fields will create, right? So this will be the direction of field because field needs both positive as well as the negative charges, right, to terminate. So you can clearly see how the field has been created over here, right? So now to create the inversion layer, I know my Vg has to be negative, right? And how negative? You must have seen this condition. Vgs should be greater than Vt. This was for the NMOS, right? Now what I will tell you over here, now your Vg, right, Vg minus Vs, right, you know Vg is negative, right? Vg is negative. So now your Vt, like your Vt is there, correct? Your Vt is also negative, correct? So this is the condition for the PMOS. So just to explain you in a simple manner, let's say my Vt for PMOS is, let's say, minus 0.7 volts. Now unless and until my VGS for PMOS, right, my VGS for PMOS, the magnitude of it becomes greater than the magnitude of Vt of PMOS. Unless and until this condition is satisfied, right, I won't be able to create the inversion layer of holes over here, right? So this is a condition that they were asking me actually. And just to give you a quick hint, if I apply a Vg of minus 0.1 volt, then I am just in the depletion region case. I have not created the inversion layer. If I apply a Vg of minus 1 volt, then I have created the inversion layer. And it makes sense, right? I already told you, the more negative you make this VG, you will get this inversion layer over here, right? So the more negative I make the VG, this -1 volt, if I even increase it, right, so it should be increased up to such an extent that it should be more negative than the threshold voltage of the PMOS, right? So now this is a condition that we need to satisfy. The VG, the magnitude of the VG has to be greater than the VT PMOS. Assume that the source is grounded. Assume that the source is not grounded. Assume that the source is connected to the VDD. Right? So now we have to just see this condition that your VG has to be more negative than VT PMOS, and you will be easily able to see over here that the VG is having more negative value compared to the VT. Right? So this is the first option that is satisfying the every condition, and this was not multiple correct answer, it was just a single correct answer. So the first option is satisfying the condition, right? So I hope this point is very much clear. If you have any doubts, then please feel free to poke me at any point. Okay, now coming to the next part, given below are the two statements regarding the ID, the current in the PMOS and the NMOS devices, right? Assume that the applied and threshold voltages of both the devices have same magnitude. What does this mean? So there is something term called as the VGS minus VTH, right? So now if I just take it, then what they are saying for NMOS, VGS minus VTH, and for PMOS, VSG minus mod VT, right? So now both these terms are same, actually they are equal. So now they are given two statements. First is the drain current of NMOS device is greater than the drain current of PMOS device. That's the first condition. The second is the mobility of PMOS device is less than the mobility of NMOS device. So now what I have to do? So I have to check whether the drain current of a NMOS device will be greater than PMOS device or not. So now let me write the equation. ID, let's say for NMOS, right? It is nothing but half mu n Cox W by L into VGS minus VTH the whole square. This is for the saturation case, right? And now ID of PMOS will be what? See, the carriers were electrons in the NMOS. The carriers over here are holes, right? So I have to write mu P, right? And VGS minus VTH, you can replace it with VSG minus mod VT, because VT is negative for PMOS, right? So I have to put mod VT over here, and this is the square. So let's say this is equation number 1, this is equation number 2, right? So the W by L ratios are same for both of them, right? It has been given in the question that they have same W by L ratios, and even their VGS minus VTH and VSG minus VT mod VT is same, right? So if I just divide these two equations, right? If I just divide these two equations, what I will get? ID of N divided by IDP, you will just get it as mobility of electrons by mobility of holes, right? Now what happens? See, the mobility of electrons, it is always greater than the mobility of holes for most of the semiconductors, right? So by default, if I have a same MOSFET of same width upon length ratio, and their overdrives, that is VGS minus VTH and VSG minus mod VT are same, then I can easily say that the IDN, that is the current flowing through the NMOS, will always be greater than the current flowing through the PMOS, right? So now I already told you there was something term called as the GM, right? GM is nothing but your dou ID by dou VGS, correct? So now if I tell you that ID is higher for the NMOS, right, compared to the PMOS, then the GM, that is the GM of the NMOS transistor, will also be higher than the GM of the PMOS transistor. And that is why you will see in most of the cases in the circuits and everywhere, we generally design the amplifiers using the NMOS and not in the case of the PMOS. It is not that there are not circuits with the PMOS transistor, but they are designed for different specifications. There are a lot of specs that you have to meet, right? There is something called as the linearity, there is something called as the noise, right? But if you just focus on this gain term over here, then we generally design most of the circuits using the NMOS transistors, right? So if you open any circuits book, you will find a lot of NMOS amplifiers compared to the PMOS amplifier, and this is one of the reasons. So that's why I just took this example. I just took this problem, the MCQ type of question, just to give you a hint of why this GMN is always greater than GMP, right? So I hope this question is very much clear. Please feel free to ask me if you guys have any doubts. Now coming to this problem number 4, right? So now let's see what has been given. So what is this Kn dash over here? In many textbooks you will be seeing this term. This is nothing but mu n into Cox, right? So they highlight this term as a Kn dash, or sometimes they highlight this term by Kn also. So now they have given the value of mu and Cox, they have given the omega by L, they have given the Vt as well, right? So now they are asking the formula for the drain current, right? So now first of all, they have given me the value of Vgs, they have given me the value of Vds. So I already told you, like there has to be one condition, Vds has to be greater than Vgs minus Vt. Only then I can use the formula for saturation, right? And if my Vds is less than Vgs minus Vt, then I have to use the formula for the linear region, right? There were two current formulas that we had seen, right? So now let's check what is the value of Vds. Vds is 1.2 volts, and what is the value of Vgs minus Vt? Vgs has been given as 0.8 volts, Vt has been given as 0.4 volts. So my Vgs minus Vt is 0.4 volts, right? So now you can clearly see the Vds 1.2 volts is greater than Vgs minus Vth. So my transistor is clearly operating in the saturation region, right? So I hope till this point it is very much clear, because you just can't use any formula, right? You have to be very sure in which region your transistor is operating, right? So now I will use the formula for saturation region now, correct? So now what is the formula? ID is nothing but half mu and Cox W by L Vgs minus Vth the whole square, right? So now let me start substituting everything. The value of mu and Cox has been given to me 0.81 milli, right? So 0.18 milliamperes. W by L has been given to me, right? It has been given as 8. And what is the Vgs minus Vth? We just found out 0.4. It is a square. So if you just calculate this value, right? This value will come out to be around 0.1152 milliamperes. Again, a very easy question. We needed to check these conditions, right? Vds and Vgs minus Vth. We found out the MOSFET is operating in the saturation. We took the formula and we substituted and we got the answer, right? So the option number B is the correct option over here. So now moving on to the next part, that is about the channel length modulation, right? So I told you, right? I will come back to this point later. So now we have seen this, right? This channel charge, right? What is this channel charge? It is nothing but, you can just see this Q is nothing but Q is nothing but C times V, right? So your Q is proportional to the voltage that is applied between the capacitor, right? So let's say this is my capacitor, right? So the more and more voltage you apply across this capacitor, that you can see over here, the more and more charges you will accumulate on the plates of the capacitor, right? So I hope this point is clear, and that's why this channel charge is in this proportional to this Vgs minus Vt minus Vx. And I told you, if you keep on increasing this Vx even beyond Vgs minus Vt, right? If your Vx becomes greater than or equal to Vgs minus Vth, then your channel charge actually reduces to 0, right? And if you keep on increasing it further, then this channel, right? Let's say this channel initially it was looking something like this, right? Now you can clearly see, now this channel, first of all, it will reduce down to just single point over here, and we call this point, right? We call this condition as pinch off. Why pinch off? Because your channel has just reduced to a single point at the drain, and if you keep on increasing your VDS value even beyond that point, then your channel actually starts to shift to the left side, right? So you don't have a channel. This delta L that you are seeing over here, currently no channel exists. No channel exists in this region. The only channel that you have is in this region, right? In this particular region, and the new length of the channel is now L minus delta L, where L was the original length of the channel that you had. So you can see this L value, it was starting from the source over here and it was ending at the drain over here. So this is what my original channel was, right? And this delta L is what my channel has shifted now, because I am applying a particular value of VDS over here, and now this VDS value became so high that the channel charge reduced to 0 near the drain end, and my channel is now shifting to the left side, right? So now because that happened, my channel length has actually reduced now, right? Now the first question that I will ask you, what happens when the channel length reduces? If I just move back to the last numerical, this is a formula that I had used, right? This is a formula that I had used. There was W by L ratio, right? My ID was proportional to W by L, right? Let me write it on the next page only. My ID is proportional to W by L, and if my length reduces, then my current will actually increase, right? This is the hint that you get from this equation. If my L keeps on decreasing because of the channel length modulation effect, then my current should increase. So this is the first hint that we get from over here, right? So now let's see whether this thing is true or not, right? So this is what I was saying over here. So this is the modified current. This is modified current. This is my modifying current, like it is taking into account the channel length modulation. So let me write this channel length modulation as CLM, right? So it is taking into account the channel length modulation, and this ID that you are seeing over here on the right side, right? It was the original current without channel length modulation. Original current, and I will just write it over here. It is without channel length modulation, right? So now what you can see over here, I already told you L minus delta L, right? This value will be smaller than L. If this value is smaller than L, that means my ratio is greater than 1, right? So L upon, so I will tell you L upon L minus delta L is always going to be greater than 1, right? So my modified current ID dash is always going to be greater than my original current that I had thought, right? And this is what sir must have told you, the channel length modulation actually increases the current, right? So now we will be solving few numericals based on this. I won't go into the details of the derivation of this formula. I don't know whether sir has derived this formula or not, but it is looking very similar to the body effect, right? It is looking very much similar to the body effect formula. So now what does this formula tell you? It tells you if I apply a particular VDS, what is this delta VDS that you are seeing over here? It is nothing but VDS minus VDSAT. And VDSAT I already told you, right? This VDSAT is nothing but your VGS minus VT. As I keep on increasing the value of VDS, right? As I keep on increasing the value of VDS, my channel will start to shift on the left side. And I already told you, if this happens, then your modified current will be increased. So let's see what happens in this formula. So if your VDS increases, if your VDS that you are applying is increases, then your delta VDS will increase, right? Then your delta VDS will increase. If your delta VDS increases, then this bracket that you are seeing over here, even this will increase, and this bracket is directly proportional to the delta L, right? So by increasing the VDS, you are actually increasing the delta L, and by actually increasing the delta L, you are actually increasing the modified current. So this is what I wanted to tell it to you, how increasing the VDS is increasing the current actually, right? So this is the analogy that please remember it, and this was the formula that I was telling you about, the modified formula of the current including the channel length modulation. It is same, Kn dash is nothing but mu n into Cox, right? Half into mu n Cox W by L, VGS minus VTS the whole square, and this 1 plus lambda VDS, this term that you are seeing, this is the only extra term that you have, right? And now you will ask me what is this lambda? Lambda is nothing but your delta L divided by L, right? And delta L I already told you, right? The delta L is nothing but the by how much distance the channel has been shifted. You don't have any channel over here, so this is the value of delta L that you have, right? And how to calculate this delta L? You have a formula over here, right? This is the formula that I was talking about the delta L, right? So I hope till this point it is very much clear to you about the delta L. Now coming to a next point, like you will ask me, okay, this is theoretical, it is sounding very much cool, right? Now what actually happens experimentally? So now this is what you will be seeing experimentally. This is your experimental ID versus VDS curve, and this is your theoretical. And what theoretical? So there is no channel length modulation over here, and the channel length modulation has been accounted over here. And how to identify? The moment you have been given this ID versus VDS characteristics, you should be able to identify whether that MOSFET has the channel length modulation effect taken into account or not. See, I already told you, as I increase the VDS, right? You can see over here. Let me just write this equation again. So this ID dash I already told you, it is nothing but your half mu n Cox W by L, your VGS minus VTH the whole square into 1 plus lambda VDS. Now this ID dash has some dependence on the VDS, right? It has certain dependence. So if I keep on increasing the VDS, I should be able to see some change in the ID. But what you are seeing over here, your ID is completely flat. It is not dependent on your voltage between the drain and source, right? But if I keep looking at the left diagram, you can clearly see that this curve that you are seeing over here, actually it has a particular slope. It is not completely flat. This curve that you are seeing, it has some increasing nature, right? As I'm increasing the VD, my ID is actually also increasing. So initially it was at this point, and whenever I reached over here, actually my ID got increased by this factor, right? So my ID is increased over here, right? So this is how your curves are will look actually experimentally on the left side. And if we just assume ideal MOSFET without channel length modulation, then on the right side the curve will look something like this, right? So I hope till this point it is very much clear. Now we will just solve few numericals based on the channel length modulation. Please give me just 1 minute. Yeah, so now we will just solve few numericals based on what I have just told you, right? So now this was a question that came in the GATE exam, and what it is, an N-channel enhancement mode MOSFET. Already told you, most of the MOSFETs that you are studying, they are enhancement mode MOSFETs, right? Don't worry about the depletion mode as of now. Is biased at a VGS greater than VTH and VDS is greater than VGS minus VTH. So what is this region? This is nothing but your saturation region. So my MOSFET is operating in the saturation region, right? Where VGS, so they have just highlighted what is VGS and what is VDS over here and what is this VTH, right? Considering the channel length modulation effect to be significant, the MOSFET behaves as. So now they are asking whether it behaves as a voltage source or whether it behaves as a current source. Now I will take the help of this diagram on the left side that you are seeing, right? So now if you look on the right side, if I take this region, right? If I just draw the line and I just want to look on the right region, right? Just we are just this only this region has been of interest to us, right? I don't want to look at this region, correct? I don't want to look at this region. Now if you look over here, my ID is exactly remaining constant. My ID is remaining constant independent of what voltage I am applying. And what is this? This is a current that is flowing between the drain and the source, right? This is ID and this is VDS, right? So now if I just draw very quick, what you can say, a quick cross section of the MOSFET, right? So now this is the my drain VD, this is my VS, right? And this is a current that will actually flow, right? This is a current that will actually flow between the two terminals. So I want to check like how if I am applying a voltage between the two terminals, how it is affecting the current that is flowing between the two terminals, right? So now if you look over here, my ID is exactly constant. It is not even changing by a bit. So if I take ideal MOSFET with no channel length modulation, then I already told you what is your ID versus VDS. It will look exactly constant after a certain point, right? Let's say this is my VD side, and if I look at this right side, let's say don't look at this region, just look at this region. My ID is not changing by even changing the voltage. Now if I just look at a current source, just remember your electrical networks, right? What is the ideal current source? What is the definition of ideal current source? So by applying, let's say this is my point A, this is my point B, this is my IAB, and this is my VAB, the difference, right? So what is the ideal current source? IAB, that is a current does not depend on VAB. I hope you remember this from your electrical networks, right? Any voltage I apply between the current source, its value should not change, right? And this is what the ideal MOSFET is telling us, right? The current is not changing despite the fact that I am changing the voltage between these two terminals. So this proves you that ideal MOSFET behaves as constant current source, right? And only in the saturation region, not in the linear, only in the saturation region the ideal MOSFET behaves as a constant current source, right? Now what happens in the case of a channel length modulation, right? So now let me just draw the quick diagram again. ID, this is my VDS, right? So this is what I will be getting, and if there was no channel length modulation, then the curve would have stayed flat, right? Now this is the region that I will call as a VD sat. Now you can see as I'm increasing the VDS, my current is also changing over here, right? So now if I just take a, what you can say, a non-ideal current source, then how do you represent it? You have certain current IAB, you have a certain voltage that you have across the current source called as the VAB, and you have something called as the R0, that is the internal resistance of the current source, right? Now if I start changing the VAB, right, let's say this resistance is 1 ohm, and my VAB, let's say I have increased it from, let's say, 5 volt to 10 volt, right? Now you know some current will flow through this internal resistance as well, right? Let me call this as IS. Now the current that will be available for the use will be nothing but IAB minus IS, right? So now my interest is IAB minus IS, because this internal resistance will actually consume some current, right? So IAB, let's say this is my, let's say, for example, let's say this is my 50 ampere, right? And now I'm applying a 5 volt over here. So for VAB equal to 5 volts, what is actually happening? What is actually happening? My IS will be what? By Ohm's law, it will be nothing but 5 divided by 1. It is nothing but 5 amperes. And for VAB is equal to 10 volts, my IS will be what? 10 volts divided by 1 equal to 10 amperes, right? So my IAB minus IS, right? So now it will actually vary from, you can say, 50 amperes minus 5 amperes, right, to 50 minus 10 amperes. So that means it is actually varying from 45 to 45 to 40 amperes. So what you can see over here. So now the reason to do all this exercise was to just prove you that for non-ideal current source, if I change the voltage across this current source, if I change the VAB, then the current that I am getting, even that will change. This was not happening for the ideal MOSFET, right? For the ideal MOSFET, I already told you it was independent, right? IAB does not depend on the VAB. But over here, the current that I'm getting out of this current source, because it has certain finite input resistance, right? Internal resistance, my current is also changing despite the fact that, like, my current is changing because I'm applying a particular voltage over here. If this voltage changes, then even my current that is available, even that will change. And this is what this behavior is actually showing, right? This is what this behavior is showing. The amount of current that I am having, actually it is changing with respect to the voltage that I'm actually applying over here. So what does this tell you? Like, this MOSFET, this, from these characteristics, I already told you that this characteristics is looking very similar. Like, if you look at this experimental characteristics that I had shown you just few slides back, right, you will be easily able to see that this has certain slope over here, right? So what does this mean? This clearly proves that this MOSFET is actually behaving like a constant current source, but it has certain internal resistance with it. So this is the MOSFET model for the case when it is operating in the saturation, right? For the saturation, and now with channel length modulation. Correct? I hope this is very much clear to you. Now let's move back to the question, right? So what they were asking, considering the channel length modulation effect to be significant, the MOSFET behaves as, right? We already just proved you, like, it is behaving as a constant current source, but it has certain output impedance, right? It has certain internal resistance with it. So now it is not behaving as a voltage source, it is behaving as a current source with finite output impedance, right? Because it is operating in the case of the channel length modulation, right? It is not the ideal MOSFET. So this is very much clear to you. Again, a very good question appeared in the GATE 2017, right? And now this is done. And now we will just finish off this numerical and we will take a short break, short after that. So now let's move on to this problem number 6, and let's see what this problem is actually asking us. So determine the increase in the drain current due to the short channel modulation. So now what does this mean? I already told you this is my original current. This is my original current. And this is my modified current, right? Modified current because of the channel length modulation. Correct? So now they are asking us to calculate this modified current value actually, right? So now consider a n channel MOSFET. They have given us the substrate doping, they have given us the threshold voltage, they have given us the channel length, right? So this L is nothing but 1 micrometer. The device is biased at VGS equal to 1 volt and VDS equal to 2.5 volt. determine the ratio of actual drain current compared to the ideal value. So now they are asking not ID dash but ID dash divided by ID, right? So we'll be using two formulas that I had just explained you in the last that channel modulation slide, right? This is the first formula, and we want to calculate the value of delta L, right? So this is the formula that we will be using for delta L. Again, I told you like I won't go into the derivation of this as of now this stage, but you can just see that this is looking like a body effect kind of formula, right? So now let's see whether we can calculate the delta L or not, right? So to calculate the value of delta L, I first have to know everything in this equation, right? So now let me try to calculate everything. So let me highlight this as equation number 1. Let me highlight this as equation number 2. So now how to calculate VDS sat? VDS sat is nothing but VGS minus VT, right? Sir must have told you this, and even I have explained in the today's lecture. So what is VGS minus VT? 1 minus 0.4. It is nothing but 0.6 volts, right? And what is the delta VDS? Delta VDS is nothing but how much VDS extra you are applying above this VDS saturation, right? How much extra VDS you are applying above this VDS sat value. So now what is the VDS they have given me? 2.5 volts. And what is the VDS sat value? It is 0.6 volts, right? So this value will come out to be around 1.9 volts. So now I know VDS sat, right? I know delta VDS, I know VDS sat. I know the Na doping concentration as well. But only thing I don't know is 5 FP. Right? And is there any way to calculate the value of 5 FP? Of course, we have calculated it 100 times, right? What is a 5 FP formula? It is nothing but your KT by Q ln of Na by Ni. Right? Na, because in NMOS you have a P-type substrate, right? You have a P-type substrate, correct? So that's why you have a Na over here. So now let's see what is the value of 5 FP. So 5 FP is what? 0.0259 into ln of, what is the formula, what is the Na value they have given to me? 2 into 10 to the power 16. What is the Ni value? 1.5 into 10 to the power 10. Now if you calculate this value, right, this value will come out to be around 0.3653 volts. So this is the value of 5 FP that I have with me now, right? And now let me highlight this as equation number 3. So now I have everything to calculate the delta L now, right? So what I will write, so from 2 and 3, we will calculate we will substitute everything in the formula of delta L, right? So now delta L is what? Root of 2 into epsilon S. Epsilon S is what? 11.7 into dielectric constant of free space, right? 8.85 into 10 to the power minus 14, correct? Divided by, I have Q into Na. Q is 1.6 into 10 to the power minus 19. Na they have given me 2 into 10 to the power 16, right? So we have this term over here, and now we have to calculate this square root terms, right? So now what we will write, root of, what is the value of 5 FP? 5 FP we have already calculated, 0.3653 plus what is the value of VDS sat? It is 0.6 volts. And what is the value of delta VDS? It is 1.9 volts, right? So plus 0.6 plus 1.9 minus root of 5 FP plus VDS. 5 FP I already know, and VDS sat is 0.6, right? So it is 0.3653 plus 0.6. So now if you calculate this value, delta L, a big equation, right? So now this delta L value will come out to be around 1.807 into 10 to the power minus 5 centimeters, or you can also write it as around 0.1807 micrometers. Now just to highlight how significant is this, my L was 1 micrometer, right? So my L was 1 micrometer. So if I just quickly draw a cross section over here, this is my N plus, this is my N plus, this is my P-type substrate, right? Correct? So now if I look over here, this was my L value, right? L was 1 micrometer. And now what I am telling, my channel will be now pinched off, right? So what do I mean by that? So if I tell you my channel is pinched off, that means my channel is only up to this point, right? So this is my channel and this is my delta L, correct? So now this delta L, right? This delta L is around 0.18 micrometer and this L is around 1 micrometer. So now if you just try to calculate, right, this 0.8, so now this movement, that is how much of the channel got shrink, right? So now how will you calculate it? Delta L by L, if you just calculate 0.18 by 1, so this comes out to be around 18%. This is not a small value, right? So my 18% of the channel has actually shrink now, correct? So this is why I wanted to tell you the numerical, to just to give you feel like by applying a particular VDS value, like how much percentage of the channel got vanished actually in this particular region, right? So now it comes out around 18% over here. Now, but our numerical is not finished yet, right? Because we had just calculated the value of delta L, right? We want to calculate the value of ID dash over here. ID dash is nothing but L upon L minus delta L. So what is the ID dash? ID dash upon ID is nothing but your L upon L minus delta L. So what is L? L is 1 micrometer. 1 micrometer minus delta L. Delta is what? Your 0.18 micrometers. Right? So now if you calculate this value, right, this value will come out to be around 1.22. Now what does this mean? Let's say you calculated without considering the channel length modulation, you calculated ID as maybe 1 milliampere. Then if you take into account the ID, the channel length modulation, now you will get the current as 1.22 milliamperes. So this is without channel length modulation and this is with channel length modulation. So you can see how much error you are getting. Let's see. So if I just calculate the error, right, 1.22 milliampere minus 1 milliampere upon 1 milliampere into 100. So this is the percentage error, right? So this is a percentage error formula. So now if you just look at this error, so now what does it tell you? 0.22 by 1 into 100. So almost 22% error. So this is why you just cannot ignore the channel length modulation, right? This is not a small error. Come on, yeah. I mean, 22% is too much, right? If you take any value, if you just try to calculate the gain of the circuit, and if you miss this current by 22%, then your entire calculations will go in on toss, right? So that's why the CLM is so important. CLM is important. You just cannot ignore it, right? So I hope this numerical just gives you a feel of why this CLM is important and how much error you will occur in the numerical if you just ignore the channel length modulation effect, right? So now this is just a very small question, but we will take it after the break. So we will take a quick 5 minutes break now. So we will get back at 7:22 p.m. So the break starts now. Yeah, we are good to go. Are you able to see the problem number 8? Okay, great. So now let's look at this question now, the problem number 8, right? So now what has been asked in this question? So in again it is taken from the exercises of Donald Newman. An N-channel silicon MOSFET has the following parameters. W has been given to me, L has been given to me, and Tox has also been given. When the transistor is biased in the saturation region, the drain current, like it has been given as 0.132 milliampere at this particular VGS and 0.295 milliampere at the VGS of 1.25 volts. Now they are asking determine the electron mobility and the threshold voltage. Now this is looking a little bit different question. They have been giving us the current and the bias voltages, right? And they are asking us now to calculate the mobility and threshold voltage, right? So I will just write what they have given. Where is my cursor? Just a minute, yeah. So now ID at VGS of 1 volt, right? So it is nothing but my 0.132 milliamperes, right? And what is the formula? It is biased in the saturation. So half mu n Cox W by L VGS minus VTH the whole square, right? And now let me substitute because VGS has been given to me for this value, right? So 0.132 milliamperes is equal to half mobility I don't know, right? Even the Cox we currently don't care as of now, into W by L into 1 minus VTH the whole square. So this is the first equation that I have. Similarly, I can write same for the second condition, that is 0.295 milliamperes, right? 0.295 milliamperes is half into mu n into Cox into W by L into VGS minus VTH. Now it has been changed to 1.25 volts, right? 1.25 minus VTH the whole square. Correct? They have not given anything about the channel length modulation, so we can easily ignore. Now we have to find the mu n and we have to find the VTH. Now the best way, so first of all, if I want to find the VTH, then I have to solve these two equations, right? Now how to do that? If I just divide these two equations, then everything will get cancelled. I will be just left with the 1 minus VTH the whole square upon 1.25 minus VTH the whole square, right? So now let me divide it. So divide 1 and 2. So if I just divide it, 0.132 divided by 0.295, this will be what? Now I will be just left with 1 minus VTH upon 1.25 minus VTH the whole square, right? This is what I will be left with. So now if I just try to solve it a little bit, maybe I will just take the square root on both the sides, and after that you can solve this question, right? 0.132 upon 0.295, this is my square root, right, is equal to 1 minus VTH upon 1.25 minus VTH, right? So if you just do some cross multiplication, if you try to solve it, right, you will get the answer of VTH as around, it will come out to be around 0.4948 volts. So this is what you will be getting, the answer for the VTH. Now how to find the mobility? Let me denote it as equation number 3, right? Now how to find the mobility? If I just substitute this VTH value, just look at the equation number 1. I already know the value of VTH, right? So if I know the value of VTH now, then I can easily calculate mu n over here, because omega by L I know and Cox we can easily find, right? So now how to find the Cox? Because Cox value has not been given to us. So Cox, it is a standard formula, right? Epsilon ox by Tox. So this is a value we know. So we can easily find the Cox value. So similarly, I will just find the Cox value over here, because it will become very much easier for us to do this numerical. Sorry, to complete this numerical. So epsilon ox is 3.9. Now what is the dielectric constant of the free space? 8.85 into 10 to the power minus 14. What is the thickness of the oxide that they have given? So the thickness of the oxide is 8 nanometer. So 8 into 10 to the power minus 7. So now this Cox value, if you try to find it out, right, this will come out to be around 4.314 into 10 to the power minus 7 farads per centimeter square. So now we know the value of VTH now, we also know the value of Cox now. By the way, this is not Cox, this is Cox dash, capacitance per unit area, right? So now we know this value. So now let's put this in the equation number 1. Let's substitute it over here, correct? So now put 3 and Cox dash in 1, right? So now what we will get? So we already have 0.132 into 10 to the power minus 3, because it is a milliampere, right, is equal to half into mu n value I don't know, the Cox value I have just found out, right, 4.314 into 10 to the power minus 7, half mu n Cox into W by L. What about the W by L? So W has been given as 6 micrometer, L has been given as 1.5 micrometers to me, right? So it is nothing but 6 upon 1.5, right, into VGS minus VTH the whole square, 1 minus VTH whole square. So 1 minus VTH I already found out, right, 4.4948 the whole square. Now the only thing unknown in this equation is mu n. You can solve everything, right? So if you just solve this value, then the value of mu n that will come out is around 599.428 centimeters square per volt second. I hope it is clear to you. If you guys have any doubts, then please feel free to poke me at any point, okay? So a good numerical, not very easy, not very hard. Like we just have to use two equations, divide them and find out the rest of the values, right? So I hope this part is very much clear. Now let's come to the main part, right? We still have to see one or two more concepts. That is about, one is about the substrate bias effect. Now what is this effect? So somebody was asking me why this body terminal is kept over here, and I had replied it, right. I have just answered like why we even need this body terminal. Now what is actually happening over here? So now the first question that comes in our mind: what happens if I know there is a N junction, N plus and P is there. So this is a PN diode over here, right? So if I apply a negative bias over here, then what is going to happen, right? So now the first thing that you should understand is the energy band diagram, right? The energy band diagrams that you draw, they are drawn always with respect to the energy of the electron, correct? And now energy of the electron is equal to minus q times v, right? Now energy of the electron is equal to minus q times v. Now if you apply a negative bias, right, if you apply a negative bias, then this minus q into minus v will become positive. It will become positive, right? And now you must have seen the diagram that sir must have told you, right? So now how does this diagram look? So if I just draw a diagram like this, right? So let's say this is my n plus source side, this is p, and this is n plus side, correct? This is my source and this is my drain, right? So the electrons from the source actually want to flow through the drain, but for this they have to cross this barrier, right? Now what I am doing, see, I already told you, like if I apply a negative bias at this body, then what I am doing, I am actually pushing the energy up for the electron, right? So if I have a diagram that is looking like this, let me highlight it over here again. So if this barrier is like this without any bias, let's say without VB, right? So that means VB is equal to 0, correct? Now if I apply a negative VB, then what is going to happen? This barrier is going to increase. This barrier will actually increase, right? So yeah, yeah. So this barrier will actually increase, right? So now because this barrier has increased over here, now electrons will find it difficult to cross it and to move into the drain region, right? So what does this intuitively tell us? If I increase my VB, negatively, right? If I so then what is going to happen? My threshold voltage will actually increase. And why is it so? Because my barrier height has increased now, and because my barrier height has increased, so it is like a increasing the threshold voltage, right? And now why this barrier height used to reduce initially? So when you apply Vg is equal to positive voltage, right, then you know energy of electron is nothing but minus q times v. If you apply a positive voltage over here, then the energy would have gone down, and this barrier that you are seeing over here, like it would have shrunk. Actually, this barrier. So and that's how these electrons used to find it very easy to cross this barrier as you apply more and more positive gate voltage, right? So now you have got the intuition now, like why increasing the VB negatively actually increases the threshold voltage over here, right? And now these are just the energy band diagrams that I have just shown. So on the right side, whatever you are seeing over here, it has been drawn with respect to the p type substrate, correct? And this is near the interface, right? So this part that you are seeing over here, it actually corresponds to this. So this region that you are seeing now, which I am highlighting over here now in the left diagram, the part number A. So this is the interface that you are actually seeing over here. So now because this junction got reverse bias, right? Because this junction got reverse bias, you will have a lot of band bending, right? So now this band bending, the reason is only because you are applying a very huge reverse bias, and you can clearly see the amount of band bending that you are seeing over here. Apart from this 2.5 FP, you have additional VSB over here, right? So now I hope this energy band diagram is also clear. And now coming to what happens, see, in the books it is always mentioned that VSB has to be positive. VSB has to be positive means Vs minus VB is there. So now VB has to be negative always, right? So now what happens if I do opposite? If I just have VSB as negative, then what is going to happen? Then a big problem will happen, right? Why? Because I'm making VB more positive, and if I make the VB more positive, that means actually I'm forward biasing this PN junction that you are seeing over here, right? So this will become forward bias and I will get a huge current component because of this PN junction. And now apart from the horizontal current component that I wanted, now I will also have one more current component actually, right? Maybe I1 or something. And similarly over here also, if you look, I may also forward bias this junction if I don't apply any voltage over here. So now I will have some different current components which I don't want, right? So that's why in the books it will be always mentioned that VSB has to be positive. You cannot make VSB negative, and that is the reason for that, right? So I hope this is very much clear. And this is just a formula that sir must have surely told you, like how much your threshold voltage changes when you apply a particular VSB voltage, right? So VSB is there. So this is nothing but Vs minus VB. And now VSB can only increase if you make VB more negative, right? So now let's look what actually happens. So if I make VB more negative, that means my VSB is going to increase. And now what I just told you, right? VSB, if my VSB increases, I just gave you one intuition, right? So if my VSB increases, then that means my barrier, the barrier for the electrons at the source to go into the drain region actually increases. That means this can be considered as an increase in the threshold voltage. So this is the intuition that I had given you, right? Let me just write it. This is the intuition that I had given to you. So now let's check in the formula whether it is making sense or not. So if I increase my VSB, then my intuition tells me that my threshold voltage should also increase. Now let's look over here. If I increase my VSB over here, then this bracket that you are seeing, this entire bracket will also increase. And now this will also increase the change in the threshold voltage in a positive manner, not in the negative manner, right? And now in the books, you will see something called as the body effect coefficient. And not only in the books, even on some YouTube videos you will be able to see that something called as the body effect coefficient. So this thing that you are seeing outside this bracket, this is called as your body effect coefficient, and it is highlighted by the factor gamma over here, right? So now this is the final formula that we will be using to solve few numericals, right? And after that we will end our session. So I hope you will remember this formula, right? And what is this phi fp? Phi fp is, we have seen it 100 times, kt by q ln of na by ni. Correct? The moment you know the phi fp,
yes, sir. Like I have one.
Sure.
Hello.
Hello, yeah, please ask me.
Yes, sir. So I was just saying, yeah. So I was just saying by looking the formula.
No, no, no. Now that's no, it's good that you thought like that, but in the MOSCAP, let's say this is my MOSCAP, right? So let's say this is my MOSCAP, this is my VG. You are forgetting that even MOSCAP had this body terminal. Even MOSCAP had this body terminal, right? MOSCAP had only two terminals. One was the gate terminal and one was the body terminal. So the body terminal will always be there. This body effect, this substrate bias effect that you are seeing now, it will occur for both the MOSCAP as well as the MOSFET. Correct, correct. Good that you are thinking in this direction. Yeah, no issues. So I hope this is very much clear. So now just remember this formula and we will solve few questions based on this, right? So now let's see. So now this is the first thing that they are asking. It's some MCQ type question. So they have given two statements. Again, we have to see whether which statements are correct and which are false. The source to body VSB must always be greater than or equal to 0 for an N MOSFET. So they are asking VSB has to be greater than or equal to 0. VSB cannot be less than 0, right? So this is the first statement that they are asking. And the second statement they are giving is the source to substrate PN junction must always be either grounded or forward biased for appropriate transistor action, right? Now we will go into the previous diagram, right? So now let's see the source to substrate junction, right? This is the junction that I was talking about. And what did I tell you? This has to be always reverse bias. Always reverse bias. We don't want this junction to be forward bias, right? And to do that, we have to make sure that your VSB is always positive, right? Only when your VB is negative, then only this junction can become a reverse bias, right? So now VSB has to be positive and we want this junction to be always reverse bias. Now let's go to the question. The source to substrate PN junction must always be either grounded or forward bias. See, this is a very wrong statement, right? This is a wrong statement completely. So the S2 is a wrong statement. What about the S1? Source to body VSB has to be always positive. Now this is a correct statement, right? So my S1 is a correct statement and S2 is a wrong statement, right? So now what the answer will be, my S1 is the correct but my S2 is the false, right? I hope a very easy question, right? So just you need to have a clear concepts. So now let's move on to the next numerical, that is problem number 10. Calculate the body effect coefficient and the change in the threshold voltage due to an applied source to body voltage, right? So now they are asking us to calculate the gamma first. We have to calculate the gamma, right? So now let's see how to calculate the gamma over here. So for calculating the gamma, so by the way, let's see whether they are asking anything or not. They have just given us the data of the doping, they have given us the thickness of the oxide, and they have given us the VSB of 1 volt, and they have given us the standard temperature. Now to calculate the gamma, I have a doping concentration with me. I know the dielectric constant, I know the value of Q. I don't have the value of Cox ready made with me, right? So Cox I can easily find. What is it? Epsilon ox by Tox. And what is the value of epsilon ox? 3.9 into 8.85 into 10 to the power minus 14, correct? And what is the value of Tox? The Tox is 20 into 10 to the power minus 7. So if you just calculate this value, then this value will come out to be around 1.726 into 10 to the power minus 7 farad per centimeter square. Now I have everything to calculate the value of gamma. So let's substitute each and everything, right? So root of 2 into, what is the value of Q? 1.6 into 10 to the power minus 19, right? Into epsilon S. Epsilon S is what? 11.7. The epsilon of silicon into dielectric constant of free space. 8.85 into 10 to the power minus 14. Into Na. So Na is what? 3 into 10 to the power 16, right? Now once you have that, we also have to divide this thing by Cox. That is 1.726 into 10 to the power minus 7. Now if you just calculate this value of gamma, right, this gamma will come out to be 0.5777 root of volts. Now why root of volts? See, this delta Vt has a units of volts, right? This right side in the bracket, this has the unit of root volt minus root volt, so again it became root volts, right? So from root volts I want to go into the volts, right? So this body effect that you are seeing, it has to have the units of root volts, right? So please remember this thing, correct? So I got the value of body effect coefficient 0.5777, right? Now once I have this, I can easily calculate the value of delta Vt. The only thing that I still don't know is to the value of phi fp. The moment I know the value of phi fp, I can easily calculate the value of delta Vt, right? So now let's calculate the value of phi fp. How to calculate the value of phi fp? It is nothing but Kt by Q ln of Na by Ni, correct? If I just substitute it, 0.0259 ln of, what is the value of Na that I have? 3 into 10 to the power 16. And what is the value of Ni? 1.5 into 10 to the power 10. Now if you just calculate this value of phi fp, right? Now this value will come out to be around 0.3758 volts. Now we have everything that we require to calculate the value of delta Vt, right? So this delta Vt is what? Gamma times root of 2 phi p to phi fp plus VSB minus root of 2 phi fp. Gamma we had already calculated 0.5777, right? Root of 2 phi fp. 2 into phi fp value we know 0.3758. What is the value of this VSB? VSB has been given as 1 volt in the question, right? So now 1 minus root of 2 into 0.3758. Now what this answer will come out to be, this delta Vt, if you look, this delta Vt answer, if you look, right, this will come out to be around 0.264 volts. So this is a change in the threshold voltage that you will observe because you have applied a body effect, that is VSB of 1 volt, right? So now I hope this is very much clear to you. Now we will be moving on to the last short concept of the today's numerical, that is about the sub-threshold conduction, right? So sir must have told you about this. So now what happens, ideally we have a curve like this for the ID versus VGS, what we assume, like before VT there is no current, your ID is exactly zero, right? But what happens experimentally, you will find that even if you reduce VGS slightly less than VT, you will get some finite ID. You will get some finite ID. Now we have to see the reason for that, why we will get some finite ID, right? Now if I just take the energy band diagram, right? So this is your P type substrate, right? This is for the N MOSFET. So this is for NMOS, right? So you have a P type substrate over here. If you just look at the energy band diagram, like I have a EF over here because it's a P type substrate, right? Now if you look at this interface, right? If you look at this interface, my EF, right? At interface, my EF is greater than EFI. What I told you, I'm applying a VGS, but this VGS is less than VT, right? It is not zero, it is somewhere between, it is just less than VT. And you can see with this condition, right? What is this condition? The phi FP, my phi S, that is the surface potential, right, that we had studied long back, it is somewhere between phi FP and 2 phi FP. What is this 2 phi FP? It is the condition for the inversion. So I have not completely inverted the surface yet, right? This EF is greater than EFI. This means the semiconductor material has become a N type, right? But it is not N type. Like for example, the amount of electrons that you will be able to see near the interface, they will be still in very less concentration compared to the whole concentration in the bulk. I will repeat that statement again. The amount of electron, the concentration of electron at the surface, it will be lesser compared to the concentration of holes at the bulk, right? And what does the inversion tell us? The concentration of electrons at the surface should be at least equal to the concentration of holes in the bulk of the p-type semiconductor. But what I am getting over here, the concentration of electrons is lesser than the concentration of p-type, the concentration of holes in the p-type semiconductor, right? So now, but you can clearly see this surface, near the surface, I still have some electrons, right? I still have some electrons because it's a N-type semiconductor now, correct? So if electrons are still there, right? If electrons are still there, then it doesn't make sense that the current is zero, because I have free carriers with me. The moment I apply a voltage at the drain and source, these carriers should create certain current, right? And now because these carriers are existing over here, they will create certain current even when your VGS is less than VT. Even if your VGS is less than VT, you still have some free carriers. Because you still have some free carriers, you will get certain current, and that current, when you get for the condition of VGS less than VT, is called as your sub-threshold current, right? So this is just a recap what sir must have told you, right? So this just it gives you an intuition why sub-threshold current should exist at the first place, and why these characteristics, right? This type of characteristics where this is your VT and your current is zero over here, why this is only suitable for a ideal MOSFET, not for a real MOSFET, right? So I hope this concept is very much clear. Now coming to these are just few energy band diagrams that I have drawn. You can refer to it later also. So this is nothing but my actually source region, right? This is my actually a region of the channel, and this is my drain region. This is my drain region over here. Now what I'm just showing over here, like what happens in the case of the accumulation. This is the case of the accumulation, right? This is the case of the weak inversion. Weak inversion means I have not completely inverted, right? But still there are sufficient electrons near the interface, and this is the case of the inversion region. So this is what actually I was telling you, right? So now what I was telling you, when you apply a positive voltage, your energy band diagrams actually gets pushed down, and this is what actually helps electrons to jump over here. You can see how from accumulation to inversion, this region, or this the near the gate, that is this channel, how its energy level got down, right? Because I have applied some positive gate voltage, and it further got down in the case of the inversion region, right? Because E is nothing but minus Q into V, and if you apply voltage as a positive thing, then your energy will become negative. So that's why the more and more positive voltage you apply, the more and more down this channel's energy level will get in this energy band diagram, right? So this is what I wanted to tell you. And even in case of weak inversion, if you look, you have only this much barrier to cross, right? In case of the accumulation, right, if you look, electrons had such a large barrier to cross, but in case of the weak inversion, you still have a very less barrier to cross. So some of the electrons will actually jump from the source into the channel, and they will make all their way up to the drain over here, right? So I hope this point is clear. This is the energy band perspective of the sub threshold conduction. The last time I gave you, it was just this, I just gave you the example of this p type and the surface over here, right? Why there exists the electrons over here, and why it should make sense that current is not zero. And this is the complete energy band diagram as you move from the source to the drain over here, right? So I hope this is very much clear to you. Yeah,
Yes,
please go ahead.
yeah. Sir,
Yeah. The flat band condition. Okay, this is has been drawn only for this particular. If you go horizontally, right? If you go horizontally from the source to drain, only then this diagram has drawn. To get the flat band, right? You have to draw the energy band diagram vertically. You have to draw it from vertically. So you have a gate, you have a metal over here, you have a oxide over here, you have a semiconductor over here. So this is what the vertical energy band diagram will tell you. See, there are two ways. Sir must have shown you in the 3D kind of band diagram, right? He must have shown you in the lecture, right? The 3D kind of band diagram, if I am not wrong. Do you remember that in the lecture? He must have shown you, right? I'm just taking the cross sections. This diagram that you are seeing, from this diagram you can see. See, this is the vertical. This is the vertical energy band diagram. Vertical energy band diagram means if I look at the MOSFET, if I take the vertical cut of the MOSFET, something like this, right? Then I will get a band diagram like this. But if I go horizontally from the source to drain, I will get the band diagram like this. Now coming to your point, now this bending that you are seeing over here, right? This bending you can explain with that flat band diagram and everything. But you won't get the flat band diagram condition if you draw it horizontally actually. Yeah, great. So I hope it is clear. Good question, by the way, because I had the same question when I was in BTech. Good. So now coming to the next problem. This is the last problem for today. Now again, it has been taken from the unsolved problem from the Donald demon. Right? So now I will solve for few part of this question. Few part will be left as the homework for you. Right? So now what this question is asking. Okay, they have given the expression. One more thing that I forgot to tell you, that the expression, the ID is nothing but something like IS into exponential of some, I don't remember exactly, some V by some KT by Q. And some factor will be there. So in sub-threshold, your ID characteristics, right? ID versus VGS characteristics, it is exponential. It is not square law anymore, right? Because you can see from this energy band diagram over here, right? You must have seen the minority carrier concentration. You must have seen in the PN junction, right? This, let's say this is your background minority carrier concentration, and this is at the depletion region H, right? So now this carrier concentration was proportional to e to the power q VA by KT. I hope you remember this thing. The more and more voltage I apply in the positive, in the forward bias manner, the more and more carriers, minority carriers, I will get at the edge of the depletion region, right? So just by using this analogy, you can say that this characteristic that you are seeing over here, for when the VGS is less than VT, it is exponential. The moment you cross VGS greater than VT, right, this becomes a square law. Right? So now this expression that you are seeing, this exponential, this is what they have given in the question, right? And they have given certain values over here. Now the first question they are asking is like, just look at what has been given. So this equation is only valid in this region, right? And now the factor of 2.1 takes into account the effect of interface states. I don't want to go into the details over here because it's out of scope of this course, right? Now assume that 10 to the power 6 identical transistors on a chip are all biased at the same VGS and VDD of 5 volts. Now what does this mean? In my first lecture, I must have told you that you have a something called as a silicon wafer. You something have called as a silicon wafer. After that you dice it, right? You dice it, you cut it. And this is the part, this is your chip. This is something called as your chip. And now if I zoom into it, right? If I zoom into it, then what has been given in the question? This is my VDD, right? And they are telling me you have multiple MOSFETs. And how many MOSFETs you have? 10 to the power 6. A lot, right? A lot of MOSFETs are there. Let's say this is my VDD, correct? And this has been given as 5 volts. So now, why this problem is so important? Because just understand that a particular, let's say this is a particular IC, right? This is an integrated circuit, and it has around 10 to the power 6 MOSFETs that are there in it. So let's assume that it is a very small processor. A processor normally, for example, if you look at the Apple processor, the latest processor, it has around 11.8 billion transistors, right? So now just consider this as a very dedicated signal processor, but it only has only this much MOSFETs, right? It does not have this many billions of transistors, right? So now this VGS that you are seeing, a same VGS has been applied across all the MOSFETs, right? And this VGS has been varied 0.5, 0.7 and zero point 0.9 volts. Right? So the first question that they are asking, calculate the total current that must be supplied to the chip at VGS equal to 0.5, 0.7 and 0.9 volts. So let me solve this question for VGS equal to 0.5 volt first. Right? So I already know the formula, right? What is the formula? 10 to the power minus 15 exponential of this. There was a VGS over here, so the VGS has been replaced by 0.5 over here, right? So 0.5 upon 2.1, right? So what is this VT? This is VT is nothing but your KT by Q. KT by Q. And at room temperature, it is nothing but 0.0259. 0.0259. Correct? So this ID, if you substitute and if you calculate it, right? So now this will come out to be 9.826 picoamperes, right? And it is at the VGS value of 0.5 volts. Right? So now this is for 0.5 volts. If I just calculate it similarly for another voltage, right? Another voltage, let's say 0.7 volts. So let me substitute at 0.7 over here, 2.1 and your KT by Q value over here. Now this value that you are seeing over here, this value will now jump to around 3.885 into 10 to the power minus 10 amperes. And this is when your VGS has been increased to 0.7 volts. Right? Now they are asking us to calculate the total current. This is only for a single transistor. For single transistor. Right? Now if I calculate ID total, how many transistors I have? 10 to the power 6. So ID total will be 10 to the power 6 into nothing but ID. Right? So 10 to the power 6 into 9.826 picoamperes is nothing but 10 to the power minus 12. Right? So now what did this became? This became like 9.826 microamperes. Right? This is for the first case. Right? And now for the second case, ID total, if you just do the same thing, right? 3.885 into 10 to the power minus 10 into 10 to the power 6, right? So now this will come out to be around 0.388 milliamps. This is the second thing, right? Now this was the first question that they were asking, how much is the total current that the chip must be supplied with, right? So this is the total current that let's say this is a very small processor, so this is the total current that your chip will be consuming. Right? Now coming to the second part, calculate the total power dissipated in the chip for the same VGS value. Now how to calculate the power dissipation of the circuit? See, I have a ID1, let's say ID1 dash, let's say this is ID2 dash, right? So let's say if I just sum up all the currents, right? Let's say this is ID dash. So if I multiply, if this much current is flowing through my supply, if I have a voltage source of 5 volts, right? And it is giving supply to, let's say, a black box over here, let's say my processor. Now if ID dash current is flowing through it, then the total power dissipated over here, like the power has to be conserved, right? Whatever power I am supplying over here, it will be getting dissipated over here, right? The total power that will be consumed by this chip, right? If you look, then it is nothing but your VDD times ID dash. Because from this VDD of 5 volts, I am consuming a ID dash of current, right? ID dash, this is what I am highlighting over here. So this is the total power dissipated in the chip, right? The total power dissipated in the chip, right? So now I have ID total with me. Just a minute, sorry. Something happened. Okay. Just a minute, just a minute. I just have to take one more slide. I don't have any space left with me to solve the problem. Yeah. We are ready to go. Okay. Yeah, so we are ready to go. So now let me see. Yeah, I have ID total with me. So now let's look at the power dissipation. So now what is the total power dissipation? This is I already told you, VDD into ID total. So for the first case, what it will be, VDD is constant, right? VDD is 5 volts into ID total. I had already calculated 9.826 microamperes. 9.826 micro. So now this will become around 49.1338 microwatts. And now for the second case, if I calculate it, this will be what? 5 into ID total was 0.388 milliamperes. 388 milliamperes. Now this will be coming out to be around 1.94 milliwatts. Now why this was so important? So I just wanted to tell you, if you design the processor, if you design a very small processor, let's say having a 10 to the power 6 transistors, right? And if you don't take into account these sub-threshold currents, right? So now what it will tell you, you may think that your processor may be consuming just a few watts of power, but this milliwatts that you are seeing over here, this 1.94 milliwatts, this will be out of the picture. If you completely ignore the sub-threshold current, let's say your processor will be consuming around, let's say maybe, let me just give you a quick number, maybe let's say around 200 milliwatts. Maybe around 200 milliwatts is the total power dissipation of your processor, right? And now if you just throw these numbers completely out, then you will be getting this much error. And now why these are so important? Because if these sub-threshold currents are there and you are still not taking them into account, let's say your processor is not doing any operation, but still it is consuming this much sub-threshold current, right? What is the value? Like I just told you, 0.388 milliampere across all the transistors, right? Total current consumption is this much. So your processor is not doing anything. It is still consuming this much current. What does this mean? So you have a battery over here, right? You have a battery, maybe a lithium ion battery, right? Maybe a lithium ion battery, and now it has to supply give a voltage to this processor having 10 to the power 6 transistors. Now let's say under this, like the bias conditions have been set up, like the transistors are operating in the sub threshold, and you thought that they will not consume any current because you use your ideal MOSFET model, right? But you can clearly see that they are still consuming around 0.388 milliamperes of current. So even if your processor sits idle, right? So this much current will be consumed by current will be consumed by your processor, and your battery will actually drain out, right? Because this processor will constantly consume this much current, and now you will start thinking why my battery is draining down so quickly, right? So I hope this was very much clear, and I hope today's lecture must have proved you why you should not ignore the channel length modulation effects and this sub-threshold current, because I just proved you with the numbers how dangerous this can be. So this was the last question for today. If you guys have any doubts, then please feel free to poke me any questions if you have, or else we can just stop the lecture because we are already above our time.
Yes, sir, I have just a general doubt.
Sure.
If you can clear me.
Sure, sure.
Sir, like
Just a minute. Let me stop the record. Let me just stop the recording. Just.